Alright, this is the first lecture regarding photogrammetry, and I've done it in a way that the first 5 lectures we're going to talk about aerial photogrammetry, and the remaining 5 we're going to talk about remote sensing, satellite imagery, data collection. Now please note that photogrammetry is one method of remote sensing.
This, what you see here, is our table of contents. The topics we'll cover in this first lecture, we call it Photogrammetry 101, the basics, what it is and how it works. How do we use aerial photographs in terms of acquiring the aerial photographs using aircrafts, what type of aircraft, selecting the various type, the appropriate aircraft based upon the specifications given by our clients, and also how do we come up with flight plans. There's a manual method that is before computerization, and there is a more program-oriented method that is using computers after computerization. This is a definition of photogrammetry, and it's defined by the American Society of Photogrammetry. It is the art, science, and technology of obtaining reliable information about physical objects and all phenomena and the environment through processes of recording, measuring, and interpreting photographic images and patterns of recorded radiant electromagnetic energy and other phenomena. Now, the use of photogrammetry captures, first of all, the visible part of the electromagnetic spectrum, where things that we see will be recorded on a aerial photograph. It can be stored analog, but modern day methodology stores the data on digital photographs. We can capture the visible portion, we can capture the electromagnetic portion, infrared, the different types, different portions of the spectrum can be captured in photogrammetry, depending upon what we are looking at. But popular methods of capturing data in aerial photograph in photogrammetry is using the visible portion of the spectrum, which we'll talk about in more details later on. Here you see a little mock-up diagram of Photogrammetry 101, what it involves. We have our aircraft, and this is our terrain. We are flying in the area, and photographs are taken sequentially. So there's an overlap. So this is my first photograph, and then the aircraft is flying toward in that direction. We'll have another photograph that will overlap the area, and it is the overlap area that will create our three-dimensional model, or commonly known stereo model. We would need to know the characteristics of the film, characteristics of the lens, and also make sure that the aircraft is flying within a certain specification directly over the area of interest. So it's flying vertically and capturing vertical photographs, and that's what you see in here. The camera is housed at the base of the aircraft, and the camera contains film and also the collection of lens that help focus all the light through the lens, and it'll focus it on to the film. The challenge here is for the pilot to fly the aircraft as parallel to the terrain as much as possible, and we'll go in more details into it. Here are a set of diagrams where you would see how the photographs are taken. This is an entire run. 3 photographs were taken as the aircraft fly. It's actually capturing images based upon a specific time, and also considering the flying height and also the photo scale that we want to get our photograph at. Photographs are taken out. Usually, yes, usually, because if it's not mentioned in any specification, usually you want to get a 60% overlap between photographs, neighboring photographs. So you have a 60% overlap between the first and the second photograph. Once we have those overlap area, we would use stereo plotters or soft copy workstations, which we'll explain about later on, to create a 3D model of the terrain in a smaller model of the terrain in a computer environment, from which we can trace out where the features are. Here, for example, you're seeing a road. We have a floating mark that would trace out. We would manually trace out where these are on the model, and you are actually drawing your map as you move along. How does photogrammetry work? We need to understand there are a number of procedures you need to follow in terms of acquiring the aerial photograph. So there's a flight acquisition. Also, once you get the aerial photograph, you need to go to the lab and create your stereo model, include the ground control points, define projection system, then use software to do the triangulation of all of the aerial photographs, and together with the control points that was gathered by land surveyors, then start collecting the data and editing it, etc. But all of these methods, it all depends upon what is the goal of photogrammetry, the intent of the flight. There are different goals. The intent of the flight, mapping photo only. We need to understand that we might only want to just get aerial photographs and not create a 3D model. So we might want to create also photos and use the photographs only. Mapping and photogrammetry, there are different goals in those different aspects. Or do we want to create ortho photos, which we'll talk about later on, or do we want to capture imagery using LiDAR, which is with another new technology that we're going to talk about later on. Also, another goal could be multispectral. All right, do you want to capture the visible portion together with infrared portion, ultraviolet portion of the spectrum, things like that? And we can have a combination of all of these. It all depends upon the goal of what we want to achieve in a given project. The first thing that has to be done in flight acquisition is be able to determine a flight plan for the collection of the aerial photograph. We need to plan out that in a very detailed sense what we're going to capture, what flying height we're going to ask the pilot to fly, the area that we're going to capture, the scale of the photograph. We need to anticipate good weather conditions. Type of photograph, is it going to be using the traditional analog frame camera or digital cameras? The number of flight lines in order to capture the area of interest, which will indicate the number of photographs that we need to capture. We also need to consider the targeting of the putting in ground targets, which will be placed on the ground and that are visible from the aircraft when at the time of capturing each photograph. So we want to see those targets on the aerial photographs. Those targets gonna have a ground control information. Each target's gonna have a coordinate, an X, Y, and Z value that typically the licensed land surveyor would go out there and coordinate for the photogrammetrists.
20. They brought their
the acquisition of your aerial photograph. This diagram here shows you area of interest shown here in dotted line. It's the extent of that area of interest is north-south, and the aircraft is flying from a west to an easterly direction, and then it'll make a turn and cover another airstrip along that area and then start capturing images. What you should note here between neighboring photograph there is the 60% overlap, and some instances there's also an overlap with the third photograph. And as the aircraft come to the second airstrip or run, there is also overlap, side lap, with the first run of photographs. So that's what you're seeing here. There is some overlap in this area. Once those, we try to get as much overlap as possible, because it's, we're going to use these overlapping areas to create a three-dimensional or stereo model. Here you are actually seeing the 3D model being displayed, and using specific optics, glasses, you can see 3D just like as if you are in a IMAX cinema, be able to see 3D images and trace out the features that you want to get. And those tracing of the features are actually capturing the X, Y, and Z value of those features. A few things you need to consider when you choose an aircraft for mission. There are different types. Just give you a quick introduction into how it was done long ago, so just bear with me in the following slide. Here you see an example of long ago they were trying to, they knew that people knew that they can collect aerial images, but they didn't have a proper aircraft. So what they did was try investigated the use of pigeons and strapping on cameras on their chests, and with cameras that can capture images that as the pigeon fly across the area, hopefully over the area of interest. Now these were trained pigeons, of course, and they were trained to fly a specific area, and it requires a bit of training on the part of those pigeons. But they actually during that time captured some images. Now, in terms of how useful in creating stereo model at that time, I don't think the intent at that time would have been to create 3D models, because it's very difficult to tell a pigeon, if at all, where to fly and make sure there's a 60% overlap. Yeah, let's move on then. They also explored a more common method of capturing images, where they use hot air balloons with cameras attached at the base of the basket, where there were more control in terms of the control by man, and be able to capture the images in terms of the flying height, and also be able to move that particular balloon to the area of interest. The Cessna aircraft is commonly used to take aerial photographs. It's commonly used by a lot of the companies that take captures aerial photograph. It's common. It's relatively low cost, and it captures the image very fast. So the camera is usually strapped at the base of the aircraft around this area. Okay, it has a long range in terms of being able to fly at a relatively high altitude of 22,000 feet, and also there's a limit as to how low it can fly to the ground. That's one of the limitations of using the Cessna aircraft. It is not as good as if you have a helicopter, where you can hover over the area of interest and get a more clearer, cleaner image. But again, this is one method more commonly of all of the methods. Another more popular and more expensive way of collecting aerial photograph is by using helicopters. Now, the benefit of using helicopters, they typically can do the same thing like your Cessna aircraft. However, one of the main benefits is the ability to hover over the area of interest. and make sure that there is an overlap in the area that you want to capture, and you can move one photograph over to the other. Of course, this is going to be much more expensive, and a limitation of this is that the aircraft cannot fly at very high altitudes. So at low altitudes, helicopters are preferred, even though it's much more expensive. And in this photograph, you can see the camera being placed at the side, and also below of the helicopter, where the photographs are taken. Now, there are a number of shortcomings with the helicopter. Exposed camera, which is concerned because the camera is very expensive. As you can see here, the camera is at the outside of the aircraft, so it's exposed, and this is an expensive equipment. So you're a bit concerned about the effects on the weather, on the camera, things like that. And when the aircraft is landing, a big concern in terms of making sure that that camera is not damaged. Also, the altitude is very critical. We want to make sure that its percentage of flying height is maintained in terms of making sure that we fly at a constant flying height, in order to ensure that all of our aerial photographs are the same photo scale. And then lastly, another shortcoming is that it has a limit as to how high we can fly. Here we have another aircraft, which is an unmanned aerial vehicle controlled from the ground. It's becoming more and more popular. You can have your camera at the base of the aircraft and fly over the area multiple times within range of the remote control sensors in the aircraft, and also on the remote control. There are a number of shortcomings in this, because you want to make sure that there is a line of sight on that aircraft as it fly over the area. And some of the equipment now have a camera where you can see the area, even though you can see the area on a monitor on your remote control, and you know exactly where the aircraft is, even though you're not seeing it directly in terms of a line of sight. Here you're going to have also a miniaturized camera at the base of those unmanned aerial aircraft, which is much more expensive. These aircraft also they're limited as to how high they can fly, in terms of the altitude. Again, this one, it can be you have your exposed camera. The camera is not actually built into the aircraft because of the small size. In this diagram here, you see a fixed wing photograph where you're using, and this is aerial photograph, diapositives, indicating the ground control. So on my photograph, I should be able to see on the photograph where the photo control points are, so that I can do my georeferencing when I'm creating my 3D model. So we have one photograph, another photograph. So this is, for example, photograph 1, photograph 2, photograph 3, and there are some overlap, some obvious overlap. Here we see an example of a helicopter photograph. It is 1 inch is equal to 50 feet, and we can see quite a lot of details in terms of the road markings and also vehicles on the road. And we can also see details as shown by this arrow here, where we can see police officer actually pulling over a car, giving them a ticket. So the scale is an important consideration, and here in a helicopter photograph, it's very detailed and very beneficial. But if I'm going to use helicopter to capture a large area, for example, the entire state of Alabama or Florida, using a helicopter is going to take a longer time, as opposed to if I'm using an aircraft that can fly at a higher altitude. Of course, at the expense of the accuracy of detail. Higher up you go, less accurate. Closer to the ground, more accurate. When you zoom in, you can actually see, using the helicopter photograph here, you can see people coming out of the aircraft. There's police vehicle. Very detailed information here. You can see a lamp post. And with these photographs, we can get a lot of details when we start plotting our maps. In this example, same example here, 1 inch is equal to 5 feet. Very detailed. And you can see even on the dashboard of the car and also the speakers at the back of the car, just to give you an example of the detail at which these aerial photographs are captured. Now, in order to capture the aerial images, or aerial photos, we need to plan how we're going to capture this. Having reviewed some of the aircraft and deciding upon a particular aircraft, the next step is to determine what is our aerial flight plan. And it's a flight plan where it was done long ago before computers. There was a manual method, and we'll go through the manual method where we use topographic map and actually draw on the map lines indicate to the pilot where the path he needs to follow in order to capture the imagery of the area of interest, and also at what flying height, things like that. And nowadays we're using computers to do the same thing that was done manually. And an example here is Track Air. But Track Air is a flight management system that is used nowadays to determine flight plans for a given project. Both flight methods are still used depending upon the budget you have. However, the before computerization method will eventually be an item of history. So long ago we used this, and it is based upon this method that the computerized method was developed. We're going to look at the first method, which is the traditional method before computerization. What they typically did long ago was get the customers or the client specification of the project. From that, they'll determine what is photo scale, what is scale at which a photograph will need to be captured. Based upon the scale and the flying height are related, which you'll see it's related mathematically later on. We can determine the flying height of the aircraft, and from that then select suitable aircraft in order to capture the aerial photographs for that particular project. Once we determine the type of aircraft, from that we'll determine the aircraft speed at which we want to capture the image, and then manually draw the flight plan for the pilot. Let's go into a bit more detail what this involves. Before computerization, no computers were being used, very little computers were being used. The company that is going to capture the aerial photograph had topographic maps from which they were able to delineate the area that they're going to fly, and based upon that they will start drawing their flight lines, or other way, well actually the correct term is runs. How many runs for that specific area? You're going to have one run, another run, and for each run you're going to have a number of aerial photographs. And this had to be done manually, computed manually in terms of the speed of the aircraft, the flying height of the aircraft, and also from that the camera need to be programmed to capture images, aerial photographs, automatically by setting a specific time. So the aircraft is going to fly on a specific line or run, and the camera, which is at the base of the aircraft, will automatically capture, for example, every 2 seconds, based upon the speed of the aircraft, a photograph will be taken out. Every 2 seconds, another photograph. Every 2 seconds, another photograph. And that is what our flight plan would typically cover. Here you see a nice graphic of the aircraft flying the area. This is the terrain, and the aircraft, we have one run here, and the number of photographs were taken out, identified, based upon the number of photographs at a specific height, constant height. In the flight plan and exercise, you would have included what is the overlap between neighboring photographs and what is the side lap of photographs from one run to the other run. Okay. Here is another diagram of the same concept, where we have a flight line and the aircraft flies along this direction, and one photograph is taken out, a second photograph, third photograph, fourth photograph, and if you notice, between the first and second there is a end lap, which is 60%, and with the end lap, for the first and second, usually the third, there might be instances where the third photograph has actually images or features in shown in the third photograph that is contained in this first and second photograph. And once the first run is done, then the aircraft will turn around and come back and capture aerial photographs for the second run. There are different types of photograph. In order to create 3D models, stereo models, we use vertical photograph. Those are the photographs that are directly beneath the camera axis. Another type that is commonly being used nowadays is oblique images. You can have low oblique or high oblique. Low oblique images does not have the horizon. Okay. High oblique, you will have the horizon showing up on your photograph. And here, another type, you can have cameras with that fans out, larger areas that moves, larger area that is not stationary, but you can capture vertical and oblique and high oblique and low oblique. The other method that we referred to earlier on was using computerization. An example here, as I said before, is called Track Air Flight Management System. It is much more than what was done traditionally, in that it does everything that was done before computerization, but also integrates with the weather data to predict what's the best time to fly. There is also the ability to repeat. If you come up with a flight plan before flying, and let's say you wanted to change from the 60% overlap between sequential photograph, neighboring photograph, I want to change it from 60 to 50, you can do that. The computer can do that for you automatically. There is no guessing on the flight line location. The system integrates with the computer that is on board the aircraft. It also integrates readily with GPS equipment that is on board. There is accurate photo center location. There is accurate overlapping of for mapping purposes to create a 3D model. So a lot of good things about having the computerized system on board. Here you see an example of a flight map that was done before flying, and each one of these lines are a run that the aircraft needs to fly, and the horizontal lines indicate the photo center of each individual photograph. So before the flight has started, the pilot know how many flight lines, where these flight lines occur, what's the percentage of the forward overlap and the lateral overlap or side overlap, how many photographs, the number of models. All of this is computed before the actual flying of the area. This is the same area being stored in the computer system, and what you see here, first day's work where the pilot would have done all of these flight lines, and each dot indicate the photograph was taken out, and the following day he would come back and start at this location here. The last photograph on previous day would have been photograph 035. The next day he would come and do flight line 10, 11, 12 until the entire project is done. So it's a good way of managing the system and storing everything. At the time the photograph was taken, everything is stored digitally on the computer. This is the final product of the map, of the flight map, where it shows all of the photographs taken for the given study area, and now it's stored digitally in the computer, and we can take this, download it in the office, and then do the further processing in order to create your 3D model or do whatever you want with the aerial photographs. This is another example of a flight plan, but what is different here is that the orientation of the flight lines are different. Instead of vertical, it's horizontal. What determines this is that you try to get flight lines where the extent of the study area determines the direction of the flight line. So in this case, the extent of this study area ranges from west to east, or east to west, whichever. Hence the reason why the lines were horizontal. In the previous example, it would have been the extent is from north to south, hence the reason that the flight lines were vertical. Here they're using different symbology indicating the photographs, and they all have the specific significance as shown here in the key. This is what it looks like in the software with some overlaid imagery. You see the aircraft actually flying along this area here with the different flight line or runs, and you can match to see where the aircraft is. Sometimes it's even real time with respect to the real life imagery in the background. This is a diagram of the aircraft integrated with some GPS receivers. So the aircraft has installed in its system a GPS receiver to indicate where the aircraft is, and that offset basically is computed to reflect where the photo center of the camera is located, because that's not where the tail of the aircraft is important, but more importantly where the center of the perspective center of the lens of the camera is at the time the photograph was taken out. This is what the software looks like. It's called Tracker Flight Planning. It can tell you, the orientation of the aircraft at the time the photograph was taken out, where the aircraft is, and the proposed flight line. A lot of good information, and it's real time, and of course it requires some training on the part of the pilot being able to interpret what these things are, but also the person who's doing the photography for the photogrammetrist also would convey this information to the pilot so that he is familiar what is expected. This is the exposure station, so the aircraft is flying in a particular direction. The first photograph is taken out here, and the aircraft is flying until it reaches second. You know, the distance between the first and second photograph is determined by the flying height and also by the speed of the aircraft. All right, so usually these things happen in about 1 or 2 seconds between the first and second photograph, second and third photograph, things like that. This concludes our discussion about our definition of trying to define what is photogrammetry. As I said in previous lectures, I would strongly recommend that you download or make copies of the handout PowerPoint presentation, and also if you want more explanation, go over the audio files attached with this PowerPoint presentation.